Good afternoon, everyone. Welcome to our webinar today in the CRM-geothermal project. My name is Simona Regensburg. I am the coordinator of the project and I'm also your host today, so I will moderate it and I will give you an overview of the CRM-geothermal project. So today it's a webinar about one particular work package. It focuses on the extraction technologies of critical raw materials. And we have three presentations here about the extraction technologies and one presentation about an overview of the CRM geothermal project. CRM stands for critical raw materials from geothermal fluids, occurrence, enrichment, and extraction. Why critical raw materials? As you probably all know, we have an increasing need for critical raw materials that comes with the transition to renewable energies and to the transition to electric cars. As you see here in the example, while the ordinary combustion car only used to have very little critical raw material implemented, the electric vehicles now need a lot of more copper, lithium, nickel, manganese, and so on. The same for example, windmills. Also, they need a lot of critical raw materials. So critical raw materials are defined by the EU as economically most important for the industry, and they also have a high supply risk. And every few years, the EU announces a new list of critical raw materials. Currently, we have 34 materials that are labeled as critical. And you see the list of these critical raw materials here. I will come back to this list a little bit later. Due to the importance of critical raw materials for the EU industry, in 2022 the Critical Raw Materials Act was announced that says, among others, that at least 10% of the EU annual consumption should come of critical raw materials should come from EU countries. And that's where actually also our project is now based on. So we want to provide the EU with a new sort of critical raw materials. On the other hand, we want to talk here about geothermal energy and geothermal fluids. As probably most of you also know, is that geothermal fluids is what is transported in the pores and fractures of a geothermal reservoir. They are the heat carrier for energy supplies. So usually we have high temperatures in these geothermal fluids. And they are a mixture of gas and liquid. The liquid is called brine, which is often very saline and contains a lot of chemical components. And the provision of geothermal energy is one of the renewable energies, and it also fits another EU law, the so-called Net Zero Industry Act, that says that by 2030 at least 40% of the energy for heat should come from renewable energies within the EU, and geothermal energy and heat pumps are also mentioned as one of these renewable energies. So with our project CRM Geothermal, where we combine both the critical raw material extraction and the geothermal heat provision, we actually answer to both of these laws. You see here on the left-hand side the idea of the project. The idea is that we extract geothermal water from a deep well, use the heat for heat or power supply, and in the brine that will eventually be re-injected into the underground, but before re-injection we can extract any critical raw material that is dissolved in the brine and provides us some critical raw material. And this attempt is very promising, not only because we get CRM, but also because as compared to traditional mining, it has some positive side effects. It has not so many negative environmental impacts like traditional mining, less energy consumption, and with this we also would not be dependent on other country. So we don't have like open pits or anything like this, but this method requires very little space, very little energy consumption, and low CO2 emission. And here in the picture, you see the example of the Insheim geothermal sites where they already extract lithium from geothermal brine. Going back to the list of critical raw materials I've shown you before. So some of these critical raw materials occur in geothermal brines at increased concentrations. I marked them here in blue. And if we look now as an example at one particular geothermal fluid, the one from the well in Großschönebeck in North Germany, you see here now in the table on the left-hand side all these elements of these critical raw materials that occur in these brines, the maximal content that we can measure here, for example, lithium 200 milligram per liters. And if we assume now or look for prices of these elements, of course, this number here in the third column, this is a number that changes very often. But so this is just an idea of a price at a certain stage. But then with this, we can calculate how much additional value would give us a well if we extract, let's say, stay on the example of lithium, if we extract all the lithium from a geothermal well. Of course, it depends on the production well. If you assume, like in the fourth column here, a production of 50 cubic meters per hour, we could, for example, get 87,600 kilogram per year lithium out of this well, and this would have a certain value. Of around 7 million. Of course, it depends on many factors, but if we would really get all this lithium out, then one well could provide 0.15% of EU's annual needs of lithium in 2030. So this is actually could be quite promising if we manage to extract as much lithium as possible. But there are some central questions to answer that we are tackling in our project, and these are which and how much of CRMs occurs in geothermal waters, how can they be extracted quickly and selectively, and can a co-production be economically viable? And so the overall question is the co-production of geothermal heat and critical raw materials an alternative to boost geothermal energy and domestic critical raw material supply? The project is a new project. It has a lifetime of roughly 4 years. Actually, we are now over the lifetime already, so we got an extension until January next year for the project. We are 20 partners within the EU, Switzerland, but also East Africa, Turkey, and Iceland. And we have 19 affiliated entities included in the project. The partners come from research institutes, universities, geological surveys, and also industry and consultant companies. We have a website, and we're happy, of course, if you have a look at this. Here's the address on the right-hand side. And here's an overview of our work packages, how we are structured. First, we are looking at fluids all over Europe, geothermal fluids, what's actually in there. We did a screening and mapping to get an overview what is the composition of this brines, especially in terms of critical raw materials. In work package 2, we look at the geological control of critical raw materials. Where do they come from? How mobile are they? How sustainable is an extraction? And then we have work package 2, which deals with extraction technologies, mainly based on lab experiments. That's where we are here today. We have an work package 4 on the environmental, social, and governmental assessments. And finally, work package 5, where we demonstrate everything on a pilot site and see for one site to apply all these the outcomes of the other work packages. Just quickly to go through all these work packages. The first one is about the database. Here we developed, or the partners developed, a fluid atlas that is online available. You can have for a couple of thousand wells within Europe. You can get the critical, the composition, the chemical composition of the brines, including, if available, the critical raw material content. Here you see the link to the website. And also within the project, there was an AI tool developed that can be used to predict lithium for geothermal wells based on the other components of a geothermal brine. And also this is online available at the website of our partner Inlecom. This is in summary what was the outcome of work package 1, and then we looked at work package 2 on the geological controls, and we considered mainly 4 different geologies in order to see why, where do these critical raw materials come from, and how sustainable would be an extraction, and how mobile are these elements. And we looked at sedimentary systems in saline fluids, something that you have, for example, in northern Germany. We looked here at lithium, strontium, and coppers, and found a strong enrichment in brines of one specific, very deep lying formation of the Rotliegend. The other geological system we looked at are volcanic regions. Here we checked systems in Iceland and Turkey, and here you see the example of Iceland, where we found that especially in seawater dominated systems, we have an increased enrichment of critical raw materials in the scales of the system, of the geothermal system. Here you see a picture of a scaling in a pipe, and this has a lot of copper, zinc, and other critical raw materials. The next geological site we looked at was the East African Rift region. We had a special focus here on rare earth elements, and looked in several field campaigns together with our partners from the University of Nairobi for rare earth elements. However, we found they not increased in these waters, but we found still good potential for geothermal energy in these brines. So this is, was still interesting. And the final geological setting we were looking at is Cornwall in UK. Here we looked at lithium in granites, a little bit also for palladium, and we found it occurs in fluids from greater depth circulating through the faults here. So this is just very brief our 4 geological sites. And now I'm coming to work package 3, where we look at the extraction of critical raw material from a geothermal brine. So this is more about the chemical engineering part. And here we are also with our webinar today. The main challenges for the technologies is that it's fast and selective. So we want very quickly to remove the critical raw material from a brine. So this is like displayed a little bit like here. If the challenge, if we have a brine that contains a lot of different salts and components, and let's say we only want to look for these yellow things, that is maybe our lithium, then we need some material and extraction method that very quickly just removes the lithium and nothing else from the brine. So this means what we need as fast and selective method. It also should be cheap and recyclable. Of course, since we are talking about geothermal systems, we need also resistance to temperature, pressure, and corrosion resistance. In this work package, we look at very different technologies. 3 of them will be shown here today. Therefore, I will not go further into these laboratory tests that we are doing in this work package, but just quickly go to the next work package, which is on the environmental, social, and governmental assessments. You see here these three fields. For the environmental aspects, we compared fluxes on the different processing steps between conventional mining and co-extractions, and these checklists that we got for the environmental risk can be found here in our report. For the social aspects, we focused on how to obtain and maintain a social license to operate. And here again, you find a fact sheet and a report that can be downloaded here if this is interesting for you. And for the governmental assessments, we did overview on legislation and regulations in the EU countries and Turkey, and that also can be downloaded here. And with this, I'm coming to the fifth work package, where we want to do the demonstration on one geothermal site, and that is the site in Cornwall, United Downs, from our project partner Cornish Lithium. And in 2024, we first went there to get information on drill cores, like on the mineralogical content of the reservoir rocks. We did a geological model of the site. We did hydraulic testing to see how permeable the system is and how the fluid flow goes. That was in 2024. And now in 2026, actually just last week, we went to the site in Cornwall and installed there a mini plant. You see this here. Used one of our extraction technology that was a manganese oxide based adsorber, and demonstrated here that we can do lithium removal. Also, at the same time, we tested another extraction technology on helium with our project partner here from GFZ. And so that's very brand new. Another webinar will most likely happen in a few months about the results of this work package. But now back to where we are today. We have now the webinar on 3 extraction technologies. And I think you have now the chance to ask a few questions. If you want, you can either raise your hand. I hope I can see it, or put your questions in the chat, and I will try to answer for a few minutes before we move on to Mustafa and his presentation. So I stop now the presentation, and I ask you if you have any questions, just let me know. Oh, it seems everything was clear. Maybe I spoke too fast, or it's too warm. But okay, if there are no questions, you also can still put it a little bit later into the chat if you have a question to me. Then good to see you, Mustafa. Hello.
Hi, Simona.
Hi. Are you ready for your presentation?
Yeah, ready. I was busy to enter the meeting. I had some trouble, excuse me, but finally I reached to the meeting.
Glad to see. Yeah, it was a bit confusing since there were different links, probably.
Yeah. I think there's a firewall. We couldn't receive the email of this link. So this is something problem about us, our institution. So there's a firewall that protects some undesirable or unwanted links. Anyway, so I can share my...
Just share. You see the green arrow? Yes, wonderful.
So make a complete... So slide change occurs now?
Yes, that looks very good.
Okay, I think I can start. Thank you, Simona, for the introduction. Good afternoon, everyone. My name is Mustafa Demir. I'm working at İzmir Institute of Technology, Turkey, West Coast of Turkey. So today I checked our CRM project. I think almost 4 years ago we already kicked off this CRM project. And during meantime, the last 4 years, so we have been working in Tuzla geothermal power plant. We are doing in situ experiments for extraction of 3 cations, lithium, rubidium, and strontium. Today, I want to share some recent results regarding with lithium, okay? Extracting raw materials from geothermal brine, opportunities and challenges. This is the title of my talk. Here is outline of my speech. So I want to give some background info about geothermal mining, then in situ experimentation of lithium uptake. We carry out our experiments in situ in the real system. Then I will mention about challenges and outlook. So in the right hand side, you see the image. So that shows our ultimate goal. We want to extract lithium from waste brine, secondary source, and use it in battery sector, using as a lithium ion batteries. Well, lithium have been produced in the world for decades, and there are two main routes to obtain lithium. First one is rock mining. Rock mining, you see the picture on the left-hand side. They are digging a hole on the earth crust, and they are doing a lot of leaching for very large volume of soil. So it is something environmentally, it has some disadvantages. For example, it has lots of carbon dioxide and emission, and it is a tedious 8 steps in the system that it contaminates seawater, etc., etc. So there is no reason to further increase of the entropy of the world by doing this. So second could be evaporation pond. Evaporation pond means that it has been done in Latin America. So there's large pool again on the earth crust and large volume of brine. So they are waiting for the evaporation of the water, then left behind a mixed salt. Then they are doing some hydrometallurgy to extract lithium out of that. So it takes a lot of time. So geothermal has some treasure. It seems it contains some treasure. So the plot on the left-hand side, you see x-axis refers to concentration of various metals in seawater, not in brine. The y-axis refers to their price. And there is a dash line, orange dash line, that separates economically feasible elements and economically challenging ones. So if you are looking, lithium is on the border. The projection of x-axis says that lithium concentration is 1 ppm. Even 1 ppm seems economically feasible extraction from seawater, but many times geothermal brine is much concentrated and rich in terms of these valuable elements. So the motivation of our research is to develop a technology using commercial chemicals and commercial mechanical equipments, and we have to make a system. The system should be integrated into real geothermal power plant. After they harvest the energy, the idea is to catch these desirable metals, valuable metals, before the reinjection system. So again, the idea is to develop the technology using commercial items. In our particular case, for our country, in Turkey, there are 63 geothermal power plants that produce electricity. Established power approach to 2,000 megawatt electricity. The ratio of the electric produced by geothermal compared to consumption of entire country is around 1.5. It is a good number. So if you look the lithium concentration lies in between 2 and 30 ppm, which is much smaller compared to other parts of the world, like Salton Sea or Upper Rhine Valley. So we have almost 10-fold lower lithium concentration. However, the amount of reinjection volume is very large. Per year, we have 2-3 billions of meter cubes of brine is reinjected. If we make a small multiplication, we see that it is possible to obtain several hundred kilotons lithium carbonate equivalent lithium out of this source. So it is quite challenging for us. So in this project, it was just at the end of the TRL value 3. So the idea is to increase to TRL 6 to get rid of that value for any technologies. We want to get out safe and sound out of this problematic TRL region. So not an easy task, because the system is quite fast, hot, salty. The concentration of lithium is very low. We have to make selective isolation because sodium, for example, is much concentrated compared to lithium, and so they have similar physicochemical properties. So make a selective isolation is really hard, and we have to integrate our system to power production. Okay, so that means in situ approach is needed, and thank God we have science to improve, to overcome these issues. So in the last 4 years, in the past we were busy about Tuzla geothermal power plant, which is quite north of our city center of Izmir. It takes almost 5 hours by car. So in the last 6 months, we found another place, which is very close to our city, so it's more practical for us, has geothermal power plant. Okay, it is located in Aydın, south of Izmir. And the brine is mild compared to Tuzla. Tuzla in Turkish means salty, okay? So in this region, the composition is a bit soft. Lithium concentration is 5, boron is 35, sodium is about 1000. It is much smaller compared to Tuzla region. Magnesium, silicium, and calcium, they are not that much high numbers. The electrical conductivity is 7 millisiemens per centimeter. Okay, so you see on the right hand side a drone image of a recently found has energy geothermal power plant. They produce 24 megawatt electricity. So the region the system is located is called İncirliova in Turkish. İncirliova means this is a land of fig. Okay, they really produce delicious fig out of this region. We are using manganese dioxide as a commercial sorbent material. Tomorrow you can order this material on the order of kilograms or tons to the gate. So it's a crystalline material. It has some ionic channels inside. The size of channel is comparable with the size of lithium in solution. This is because this is an ion sieve that removes the sodium and potassium, okay? So it is only for lithium. So if the crystal is loaded with lithium, it is called LMO, loaded with lithium. If we treat with acidic solution, hydronium ion is much smaller and much aggressive that kicks out lithium from the crystal, then it becomes HMO. HMO is ready for extraction in geothermal brine. So on the left hand side you see the crystal structure of the gamma phase of manganese dioxide. There are 1-to-1, 2-to-1 spacing for lithium. Lithium is black dot point that is inserted inside there. Then upon treatment with acid, so the lithium is moved to the acidic solution. So we have 5 steps. Adsorption, like this one. Desorption, here at the last step. Enrichment, we have to enrich our lithium concentration. Then purification, together with lithium, some other undesirable ions are also enriched in the solution. So we have to isolate lithium, then we get rid of the rest, then we precipitate them. So the product is a kind of solution, yellowish and green solution. This color most probably coming from the complex between chloride and manganese. Okay. Now you see on the left hand side plot we have enrichment of lithium concentration in this his energy power plant. Initially it was 5 ppm. So after 14 cycles of enrichment it reached to more or less 700 ppm. Together with lithium again manganese also increased. So to remove manganese from the system we used carbonates as counter ion in 3 steps because solubility constant of manganese carbonate is very low. It is easier to get manganese with carbonate form. Then we have lithium rich solution. Then using evaporator we precipitated our lithium salt, lithium rich salt, say on the order of 5 grams. We dissolve this material in an acidic environment to have a complete dissolution, then run to ICP-MS to look for what is inside. We see more lithium compared to the rest of the cations. So using X-ray diffractogram, we see that this is lithium chloride monohydrate. It is good. Then another good point is following. We apply a cyclic voltammogram to this material. I versus V, we apply a potential difference and we see whether a kind of current occurs. So please follow me with the blue line. This is ITO, indium tin oxide substrate surface. So you see there is no signal, the forward and reverse lines. But then we apply our material onto the electrode surface as a film. You see in the red one, you see a weak signal going forward and coming back, you see this weak signal again. So it is much weaker than in any straightforward CV curve, I know. But there is a response here. The weak response means we may have some lithium and lithium containing other active species and they respond quite slow. But anyway, we can conclude here that the extract we obtain from his energy exhibited an electrochemical response, in fact, which is the first step for battery applications. There are 100 steps to do a real application, I know, but this is the first and promising step for us. So from equipment wise, we have a commercial stainless steel reactor. You see on the left hand side, it is working now. You see the pressure of brine. So we made a change in the design to increase the interaction time with sorbent and brine inside. Then we developed an assembly of pumping systems, sensors, and a reactor for one single reactor for lithium. Then on the computer, we assembled it. So we provided these items at the beginning of next year in July. It will be compiled. Okay, we will have first testing at the beginning of July. Then if we succeed the first testing, we want to increase the number of reactors for other target ions like boron and strontium in his energy power plant. Now, so far we witnessed two bottleneck points in the process of the development of technology. First, the manganese dioxide powder is very fine. It's a fluffy powder, so we have quite high amount of is lost in the system. They accumulate somewhere else in the system under very high tension of brine. It should be granulated. And second, we have the cost of sorbent is very high, even much higher than the price of lithium carbonate. So this is because we have to reduce the price to make it economically feasible. The point is that we can use our natural domestic manganese ores in our country. We can see whether we can use them as sorbent material. Let me begin with the granulation. So I know you spent a lot of time for the granulation of manganese dioxide using chitosan. We did as well. We dissolve our chitosan in 3% of acetic acid. Then we include our HMO powder, fine powder, into polymer solution. We have polymer particle dispersion, acidic dispersion, and it is neutralized dropping into sodium hydroxide solution. Then we have nice droplets. Then these nice drops are dried, then undergoes cross-linking, otherwise it will be disassembled during the application. It should be cross-linked to achieve the mechanical property by glyceraldehyde. Then at the end, I have nice movie. We have nice particles, hard particles that can be reused for the application. So the particle size distribution is around 1.52 millimeters. It can be seen by naked eyes. The one on the middle, the plot, you see the sorption capacity of HMO, manganese dioxide, and granulated HMO. You see HMO, nothing surprise. We begin with 25 milligrams per gram, so it decreases when the sorbent dose increases because the number is normalized with respect to sorbent dose. This is because we see the decrease. But for granulated one, we see the sorption capacity is reduced. Nothing surprised because the active sites on the manganese dioxide surface that is sensitive to lithium is already occupied by chitosan chains, the functional groups on chitosan chains like hydroxide, like amine group. Nothing surprised. Increasing sorbent don't increase. You see the sorbent sorption capacity is remarkably reduced. At low sorbent dose, it is decreased threefold. At high dosage, it's reduced into half. For reused, you see in reused experiments, we have seen further reduction of sorption capacity because the active sites are already occupied by polymer. During the washing, not 100% of the polymer is coming out from the particle surface. Some of them remains on the surface. This is because we see the further reduction of sorption capacity for the reuse of granules. Let's come to the second point. The sorbent price is very high. So in this picture, you see polymorphs of manganese dioxide. Polymorph means you have crystals. All of them are containing one manganese, two oxygen atoms, but the spacing they are different. Spatial arrangement of these atoms are different. You see please pay attention to the bottom three one. On the left hand side we have gamma. On the left hand side we have lambda manganese dioxide. They are sensitive for lithium. Gamma is electrolytical manganese dioxide. It has 2:1, 1:1 spacing. But the one on the lambda, it has one-to-one spacing, uniform spacing, and the sorption capacity is very high compared to gamma. The one bottom in the middle, the Birnesi type of delta manganese dioxide, it is sensitive, this layered structure, it is sensitive for large critical raw materials, large group 1A elements like rubidium, like cesium, okay? So they are sensitive for these elements. You see, manganese dioxide has versatile chemistry. It has different valencies, +2, +3, +4, +6, +7. Okay, so it has some versatility. The reaction on the top, you see, if we begin with gamma manganese dioxide, treat with lithium hydroxide, one can obtain lambda manganese dioxide. We prove them. Sarah proved this reaction in her thesis, and she published in Chemosphere. So in literature, there's a claim saying that this manganese dioxide is disassembled in lithium hydroxide alkaline lithium solutions, and there are some manganese oxide octahedra. These are the chemical species. It reassembled into manganese dioxide. Depending on experimental conditions, one of the polymorphs can be controlled. This is a very big claim. It's beneficial for us. If it is so, we can find manganese from our domestic ores. Here is the list of all manganese ores in Turkey. Okay, majority of them are closed now, but they do have samples. Okay, so we provide samples from the middle of Turkey, from Kayseri. Then we did preliminary experiments out of that. I don't want to bore you with this complex X-ray diffractogram. Please follow me the bottom one, the black one. So black one, you see it contains various types of crystals. Together with pyrolysis manganese dioxide, we have goethite and hematite type of iron oxide containing compounds, and they are magnetic. So when we put magnets, they are all coming out. So we carry out hydrothermal reaction, the reaction I showed you on previous slides. Layer formation started, but since the system is quite heterogeneous, the phase change is not properly followed. Okay, so then we decided to first clean our sorbent material, natural sorbent material, then carry out this hydrothermal reaction. Then this reactions and this project is in progress now. Then I think my time is running out. Then I want to conclude my talk. The lithium chloride can be obtained from low concentration of brine from has energy geothermal power plant. Lithium concentration was 5 ppm, and we achieved more or less 5 grams of lithium carbonate. And it has electrical chemical response. This is the first time we seen from our samples, and we are happy to see this signal. Then we tried to develop an equipment for continuous process of lithium uptake, which is in progress. It will be we will get the first results next month. The granulation works for manganese dioxide. This is a surprise. Using ketosand under acidic conditions, sorption capacity is reduced, but we have to use it because the manganese dioxide is really expensive. Domestic manganese ores can be good starting point for the reducing the cost of manganese dioxide sorbent. I hope for the next meeting I can provide you more reliable and concrete results out of that. Then I want to thank my group. My group is analytical group here, geothermal brine extraction, Sarah for lithium, Jan for strontium, and Özge for rubidium. And I want to thank you for your patience and attention.
Thank you. Thanks for sharing these excellent results. Yeah, there's a first question in the chat. I just read it. It says, I cannot see the name who did it, but it says, which geological origin have Turkish manganese ores or MnO2 ores? Do you know this?
So I'm not geologist, I'm a material chemist, but which origin, I don't know. Maybe Alper is somewhere here. Alper can say something for this question that I don't know.
If Alper is around, maybe you can put the answer in the chat. Mm-hmm. That would be good. And then I think Enrico raised his hand. So Enrico, one of our co-speakers, is that right? Did you?
No, it was a mistake. I didn't
it was
want to raise. I didn't want to raise my hand. I just wanted to make the virtual applause, but I couldn't find the button.
Okay, wonderful. So I have a question, Mustafa. You mentioned at certain points that you're also planning to remove boron and rubidium from the brines. Would it also be with manganese oxide, or do you have another?
For rubidium, yes. Birnacid type of manganese dioxide, this layered structure I showed in the polymorphs, it is good and it works. In Tuzla region, we succeeded to increase 10 ppm to 18 ppm using manganese dioxide, but it is still in progress. So, but boron is something else. There are some aluminum hydroxide type of sorbent materials. So it is on the list, but we are nowadays quite busy about the first C of lithium, whether our equipment will work or not. But rubidium, yes, manganese dioxide. Boron is something else.
Yeah, it has different behavior. Very interesting. And I also specifically think there's no other question, therefore I can continue one more question. It's really great that you're looking in Turkey for manganese ore, so that you do not need to import from, I don't know, China.
Yeah.
This is, I think,
so
really.
It is heterogeneous. We have to find some mining engineers to make it clean for us. So because it's quite heterogeneous. The crystal form we are looking for is there, but it is together with something. So we have to first purify it.
But purified from other manganese forms, or purified from other?
In fact, iron oxide type of things, hematite, goethite type of iron oxide crystals.
Okay. And have you tried to see if it works maybe even in the dirty form with
Yes, we tried, we tested, but the results are fluctuating. Since it is heterogeneous, so you get sample from some big volume, it may be manganese oxide enriched, you have very good results, you are happy. That you take another sample, it is iron oxide rich, so you see sorption capacity is several ppm. So this is because it should be first cleaned before use. Yeah. Let's see, we plan to write a project out of that.
Okay, yes, sounds exciting. Good luck with that. That would be great.
Thank you, Simona.
Okay. So if there are no more questions, I don't know if I see everything all right, but in the chat there is nothing. Then thanks, Mustafa.
Thank you very much.
And maybe you can stop sharing. And then our next presentation is by Enrico Nero from University of Padua. So Mustafa, if you can stop sharing, then
I'm looking for it, but
if you have two screens, then it might be on the other screen, a red button.
Excuse me, so it is not shared now.
So wonderful. Yeah, it's fine. I think
it's fine. It's all done. Yeah. Okay.
All done. Okay. And now we have Enrico about extracting raw materials. About the multi-stage approach of selective extraction of lithium from geothermal brines. Yes. Wonderful. Okay. We can see it in presentation mode, and the stage is yours, Enrico.
Thank you very much. Thank you very much, Simona. Just 1 second, allow me to start my, because I just need to find where is the here it is. Can you see my laser pointer? Okay, ladies and gentlemen, good afternoon. First of all, I would like to thank the organizers to have provided us with the opportunity to share some of our latest results on the design of our multi-stage approach to extract selectively lithium from geothermal brines. This is an effort carried out at the University of Padua in the research group led by Professor Vito Di Noto. Then there's me, and there are other people in my group that carried out a big work on this. Before we begin, I would like to point out that during this presentation, I'm not going to deliver the specific details. Some specific details will be covered because we are planning to apply to design a patent application for that. So if you just, when I speak, I will speak about ion exchange medium without going into additional detail to protect the possibility not to infringe the possibility to patent this procedure. So this lithium extraction method that we would like that we have developed is actually a multi-step project. The idea is that we, starting from a brine, we carry out in the first project we separate the divalents. After the divalent species, typically calcium, magnesium, strontium, etc. And later, starting from this brine, we concentrate the resulting solution either using a second ion extraction medium or reverse osmosis. Once we have a very concentrated solution of monovalents, which include lithium, but for the most part sodium and potassium, we are forced to evaporate a little the remaining water, and we end up with a mixture of monovalent chloride species. Then, by using a suitable green solvent, we manage to extract selectively with a very high degree of selectivity lithium chloride. And then this lithium chloride dissolved into this green agent, we are able to precipitate. We are able to precipitate, yielding battery-grade lithium phosphate. And this lithium phosphate is going to be our final product. Why lithium phosphate? Because lithium phosphate is, to the best of our understanding, a major precursor chemical for the preparation of lithium batteries, in particular of the lithium iron phosphate batteries. So in this process, we not only start from brines, but also we aim to a commercially viable product, that is battery-grade lithium phosphate with a very high degree of purity. So, what are the advantages of this project, of this process? First of all, we have a very clear and definite end product for lithium phosphate. Second, we do not need to evaporate a huge amount of water, like, for instance, in some other approaches, like in South America. We do not produce solid wastes. Spent brine can be disposed, we don't need to throw it away, and we need very inexpensive bulk chemicals to operate. Hydrochloric acid, if necessary, sodium hydroxide, and suitable but inexpensive green solvents. The critical point here is, one of the first important things is the first step about the selective extraction of divalents from a brine that includes a lot of monovalents, a lot of divalents, and just a little bit of lithium. So first of all, here we have carried out this type of experiments on a synthetic brine that mimics a real brine of a location found in our CRM-geothermal project. So what was observed is that there is the selectivity of extraction strongly depends not only on the chemical species that we want to extract, but also on the relative amount between the amount of species in the brine and how many exchange sites we offer with our ion exchange medium. So what happens we have discovered that if we start from a brine and in a lot of brine we put very little ion exchange medium, monovalents are essentially unaffected. You can see we do not block so much monovalents, very little. Yet we block almost completely divalents. So the point here is that in order to carry out this separation of divalents, what we do, we add progressively into the brine a small amount of this ion exchange medium. Actually, we have tried adding first a little bit less, weak absorption, a little bit more, medium, and even strong absorption. So we tried to play around with how much ion exchange medium we should have placed inside. And the result is no matter what, is very, very clear. If we put a lot of brine, and inside a lot of brine, a little amount of ion exchange medium, we are very good at blocking almost completely the divalents and leaving the monovalents almost completely unaffected. So now let's try to take a look, starting from this, about the results. You can see here some of the results that we have obtained recently. Basically, here on the x-axis, we have essentially how many more exchange sites we have with respect to the total equivalent of ionic species included into the brine. And here on the left-hand side, how many cations of each species are bound. What you can see here is that lithium, in this type of approach, using this ion exchange medium, is actually bound very little. Sodium is bound very little. Potassium is bound very little. On the other hand, by a careful attention on how much and how often do we add the ion exchange medium, we can see that up to a certain level, above a certain level, we absorb almost completely the magnesium, calcium, and strontium. So, if we manage to add the ion exchange medium at the right level, we block almost completely the devalence. The result is that we obtain a selective extraction. Lithium, you can see, is almost unaffected by this type of binding. We can see that calcium is actually a little bit better bound with respect to strontium, not so much. But what we can observe without any doubt is that between lithium and sodium, lithium and calcium, lithium and calcium and sodium and calcium, what we observe very clearly, in a very evident way, is that this type of approach makes sure that you enrich lithium in the solution and you remove almost completely the devalence, both calcium and, you have seen above, strontium. So this type of approach demonstrated a very effective way to remove the devalence from the brine. Here we also have studied a little bit the kinetics. What we have studied a little bit here, we could observe that binding is completed over the course of a few hours. Yet, we have other data we do not show here, by which we can assume that this type of binding, ion binding into the medium, is extremely fast. It's not hours. Is essentially completed after 5 minutes. So, this type of kinetic approach to completely remove, to extract the ions by means of this ion exchange medium is actually much faster than that. And the other point is that even if we leave a lot of time in contact the brine with the ion exchange medium, you don't really improve so much. And you do that in a single passage. However, once you have bound the ions into the ion exchange medium, you need later to regenerate this ion exchange medium. And to do so, we have made some studies. The result is that in order to completely clean off the ion exchange medium out of the ions, you just needed to bring it into contact with let's say 2 molar concentration of hydrochloric acid. This is one part of the work that we are still working on, because it's not so easy to ensure that you have outside of the ion exchange medium always around 2 molar hydrochloric acid. So in other words, yes, you can regenerate very quickly, very thoroughly, but from a practical viewpoint, to design a reactor where you can do so, a column, takes some time. We are still working on it. It is, on the other hand, also possible to use an even higher concentration of hydrochloric acid, up to 6 molar. That's fantastic, but there are some technological challenges for that. Yet, we have demonstrated that we can use the same ion exchange mediums over and over and over again by absorbing, releasing, absorbing, releasing, absorbing, releasing, after at least 5 or 10 times. That's what we tested. However, after we have done that, we, starting from the brine, we have essentially removed the devalence, but yet we still have a lot of water and a lot of monovalence. We need essentially to get rid of the water. To do so, there are at least 2 approaches. Approach number 1, we can use another ion exchange medium that binds everything, and then we can essentially regenerate these by using a highly concentrated hydrochloric acid solution. We are working on that, but the practice is that very recently we have made some calculations, and this type of approach, while it works, it's probably not the best. Much better, in practice, if you have a lot of water with a few monovalents inside, to raise concentration, it's probably better to use reverse osmosis. By using reverse osmosis, you end up with a solution with about 2 or 3 molar of monovalents, And then the last amount, the last fraction of water, it's better to evaporate or lyophilize it. It's probably better, more energetically feasible. At this stage, we end up with a solution, sorry, not with a solution, with a mixture of monovalent chloride species. Typically, we are working with lithium, sodium, and potassium species as a mixture of dry chlorides. That's what we get. When we start, we have that most of those chlorides are actually sodium chloride, some potassium chloride, some lithium chloride. But lithium chloride, even in the best case, with some specific brines that we have still studied in the CRM-geothermal project, even in the best possible way, we never have more than 5% of lithium chloride together with, let's say, 90 to 95% of sodium chloride. Useless. This stuff is more or less useless. However, if we start from this mixture of dry chloride salts, wherein sodium chloride is by far the most present, you can use suitable green solvents. When I say green solvents, I mean I cannot disclose the exact nature of this solvent, but we can use a solvent that is, how should I say, not something special, not something difficult, not something polluting. This you should, that's enough. I cannot provide more information than that. However, by using this green solvent, we can selectively extract out of this essentially and almost quantitatively, exclusively lithium chloride. So in the end, we arrive with this solution of green solvent and have only lithium chloride. Sodium chloride and potassium chloride stay back. Now, once we have this, let's say, green solvent saturated, let's say, with the lithium chloride, once we are that, we can go to the next level. One more thing. Here, there are actually more than one solvent that can be fine. The solvent that we have been working with is not very good, has actually a low solubility also of lithium. We get probably 1 gram per 100 grams, not very much. Probably there are better solvents. Still, we are working on it. Now, let us suppose we have this green solvent, and inside we have this lithium chloride, only lithium chloride. And now we precipitate. The idea is that we have this solution of lithium chloride in this green solvent. Then we take water, we alkalinize the water, we go to pH 13, 14, something like that, and we obtain this water solution, this alkaline water solution, wherein phosphates swim. And then this green solvent with full of lithium chloride, we put inside this water solution of a very alkaline and filled with phosphate. Immediately and almost quantitatively, lithium phosphate precipitates as battery-grade lithium phosphate. Actually, at this stage, we had this nice white powder. We not know exactly what it is. Yet, we took this white powder, we filtered it, we washed it, and then we make physicochemical investigation, and that's the result. We obtain a very thin powder, something like 80 nanometers, 100 nanometers of grains. And then these powders, we made micro Raman and wide-angle X-ray diffraction. EDX and also EDX. So we observed the small grains, nice. We could see lithium phosphate, phosphorus and oxygen, no sodium, no potassium, fine. We studied with Raman, we obtained this Raman spectrum. This is exactly the Raman spectrum of benchmark lithium phosphate. We can expect that it is at least 99% pure. And then we took these white powders and we made a powder X-ray diffraction. Here is the spectrum. Once again, we were unable to detect other peaks that are not lithium phosphate. So at the end of everything, yes, we can be quite confident that this approach allows us to obtain essentially more than I would expect more than 99% pure lithium phosphate battery grade. And so at the end of this protocol, yes, we managed to obtain lithium phosphate battery grade. So first, let us review. First, we use ion exchange to get rid of the valence. Second, we can regenerate this ion exchange medium actually quite easily, even though we need to find the best way to do so in a practical environment. If we use a green solvent, we are very good to remove lithium with respect to everything else. We still need to, let's say, to find the right concentration to optimize the extraction. And yes, we probably needed also to work a little bit more to find the right green solvent to selectively extract the lithium from the mixture of lithium chlorides. Take home message. With this approach, somehow we managed to obtain battery-grade lithium phosphate. I finish by acknowledging for financial support the CRM-geothermal. I must acknowledge all the team members of the research group where I offer my services, with a particular reference to the team leader, Professor Di Noto, who could not make it. There is Enrico, there's me. I would like to acknowledge Katie, who is working with me, and also which worked in the last part of this research, the Malik Demic. And I would like to thank you very much for your kind attention, and I'm ready to take your question. Thank you.
Hi, thank you, Enrico. Wonderful. It's great that you managed now the final product already, lithium phosphate. So that's new outcome. I'm just wondering, normally lithium carbonate or lithium hydroxide are the final products. Is it that was new for me to hear that lithium phosphate is used? Do you have any information where that comes from?
About what?
That you did not use lithium carbonate or lithium phosphate, but not lithium hydroxide or lithium carbonate, but lithium phosphate as final product?
That was designed on purpose, Simona. Actually, if I can remember clearly, and Catherine, if she's here, can confirm. In let's say early January, we had a very nice talk with our friends of Cornish Limited, and they basically presented the fact that in the battery industry, looks like that lithium phosphate is really a relevant product for input. Because it was claimed, and later we checked that yes, it was right, that there is a very huge market to make batteries, and at the cathode of such batteries, the cathode material is, and we knew that, but now we are sure, is lithium iron phosphate. Lithium iron phosphate is a major family of battery cathodes that serve a certain type of applications, because not every lithium battery is the same. So it would look like that there is a huge market for batteries, lithium batteries, whose cathode is a variation or modification of something of lithium iron phosphate. To make lithium iron phosphate, you start with lithium phosphate. And so what we actually in the last few months, we have tweaked a little bit our project to see if we could modify it just to get this nice product. And yes, we did. And we did manage, actually, we were very happy, to, starting from our previous product, that was lithium chloride, we managed a little bit, and then we ended up with this lithium iron phosphate that, to the best of our understanding, is, I say battery grade, but there cannot be more than 5% of impurities. I think that it is even better, should be around 99%.
Okay, thanks for the answer. There was one more question to you in the chat from Radoslav Mukas. In your experience, what approximate lithium content in hydrothermal resources would be expected to be economically viable for extraction? If you have any specific information, thanks in advance.
Well, what I can say is that we tested this approach with a specific brine, with a synthetic brine that mimics a very specific brine that was used in the CRM-geothermal, and I do not know whether I am allowed to disclose the specific site at which this brine is found. I don't know whether I can, so I don't. What I can see is that, of course, typically what I showed, the more we have the lithium, of course, this process, you can see, works with 1 ppm of lithium per 10 20, 30 ppm of sodium. So when we have a 30-to-1 ratio, that's fine. If we have even less lithium, that is typically the case, the problem would be the final ion extraction. Sorry, the final solvent extraction. That's the problem. It might be necessary to use a two-step extraction, but to do so, I never tested. I think that it could be feasible to extract lithium according to a reiteration of this approach when you are around 20, 30 ppm of lithium. Probably. Anything more, really, I don't know.
Okay. I have one more question to you. Have you ever tried real brine or just the synthetic brine so far?
The answer is that so far we have only tested synthetic brines. Yet, for the specific chemistry that it is, for the specific chemistry we are talking about here, I am really confident that what is the difference between real and synthetic brine? The big difference, in my opinion, is the anions. Because in this specific type of approach, works very well with chlorides. Because we tested with chloride, it was all right.
Yes.
At least in that specific brine that I have been working on, there are, if not chlorine, there are halides, because if it's not only chlorine, it's chlorine plus bromine. I think, once again, I did not test yet, but I am very confident that there should not be real problem. Why? Because when I make solvent extraction with the green solvent, no matter what, you will only extract lithium chloride and to some extent lithium bromide. And then precipitation doesn't depend on that. So basically you will select first you select the anions, the cations in one way, and then you will select the anions when you make the solvent extraction. And that's the point where leads me to think that it's no big deal.
Okay, fingers crossed that it will be like that. I'm hoping to see those results as well. Thanks a lot, Enrico. I think there are no more questions to you, but there was actually one more question to Mustafa, which just appeared the moment Enrico started to talk. The question to you was, is the manganese oxide method you used, did you use it already in the pilot power plant?
Yes, we are using in the real power plant. In the pilot system, we had mini pilot system before in the past, so we are about to design the pilot system. For next month, we will do our experiments using the new and biggest pilot system.
Okay, so good luck for that too. Okay, thank you. And then with that, we are coming just slightly late, I think, to our final presentation from Saskia Bin-Schedler from the University of Neuchâtel. You're around? Yes, wonderful. So
I'm still there.
That's good. Then I hope you can share. And she will talk about using microbes to extract lithium from geothermal brines. The floor is yours.
Okay, so I hope everyone is still awake for some more scientific results. So I'm going to present here some suggestion how to use microbes to extract lithium from geothermal brines. And I think I'm not going to spend much time on it because we already discussed about that. But in this project, what we are looking for is the extraction part, and more specifically, the use of biology to extract metals out of these fluids. And specifically, our aim is really to concentrate and recover something that is initially dissolved and then transfer this into a solid state using microbes. So first of all, why microbes? Because microbes, they do this all the time. A microbial cell is a very high surface in interaction with its environment. And there are a lot of mechanisms that are being described where metals can, where microbes can either increase the solubility of a metal, or the other way around, can decrease the solubility of a metal. It can be any metal or any element. And microbes, they do this all the time, either to get nutrients or to protect themselves against the toxicity of a given compound. Of course, all of this is in interaction with environmental factors, and this is why it's not always easy to set up into an industrial context. Then, which type of microbes? Most of the time, when you say the term microbe, people are going to think about bacteria. Very importantly, we work with many different types of microbes. We work with bacteria, but the idea is also to explore the possibility of fungi, either those that are single-celled, the one that is the yellow one that is pictured here, or filamentous fungi. And then what we also would like to take inspiration from is nature. So this is a bit into the frame of these nature-based processes. And one natural mechanism that we would like to get as inspiration is the oxalate carbonate pathway. That is a natural biogeochemical process that has an impact on both the solubility of elements, but also on the pH. So I'm going to describe the pathway very briefly. It all starts with CO2 that is uptaken by plants and another type of organism, but CO2 is uptaken by plants, and then some of the CO2 is transferred or is processed and then transferred into organic acid, and one very prominent organic acid that is being produced by plant, but also by fungi. So that's a bit another type of organism doing organic acid is oxalic acid. And then oxalic acid is a very strong organic acid, and then it has an environmental effect via a decrease of the environment or the local pH, but it's also a chelating compound. And in a natural environment, oxalic acid is going to turn into its conjugated base, oxalate, and then is going to complex with various elements. The most prominent one in an environment or a terrestrial environment, let's say, is calcium. Then you have calcium oxalate. Calcium oxalate usually is or has a very low solubility, so you would expect to find it accumulated in the environment. However, this is never the case. Why is that? Because there are bacteria that are able to feed on this oxalate, and when they do so, they convert a strong organic acid into a weaker one that is carbonic acid. So there you have this effect on pH. And then if you have an increase that is high enough, you may reach the equilibrium state of carbonate and you can start precipitating carbonate. So then if I translate this into what we call a nature-inspired process, what you would have is that you would have an oxalic acid producing organism, either a plant or a fungus. In a lab environment, obviously, a fungus is much more appropriate. So then you have this calcium oxalate that can combine with an element in solution so that you transfer this element into a solid state. In the oxalate carbonate pathway that is being described in a natural environment, this would be calcium. Then this calcium oxalate is used by oxalotrophic bacteria for growth, where they convert oxalic acid into carbonate. And then you may have calcium carbonate precipitating inside. So overall, what we try to do in this project is to see whether this OCP can be applied into an industrial context for recovery of metals in the form of metal carbonate. And the element on which we focused is lithium. So the idea is really here to use this activity to, first of all, filter out a bit the fluid, but eventually to reach the pH that allows for the precipitation of lithium carbonate. So overall, the biorecovery steps would consist in, first of all, the production of oxalic acid. This is produced ex situ, so this is not introduced in a geothermal loop, let's say. Then with this biotically produced oxalic acid, you would filter or clean the geothermal brine. So use oxalic acid to chelate anything that you don't want in the fluid in order to keep what is interesting. And here is lithium. And then you would use this clean fluid to increase the pH and then precipitate lithium into lithium carbonate. The results I'm going to show now are mostly the results of one master thesis that has been carried out at the start of the project, and then the ongoing PhD thesis of Gillian Laurent. So in terms of oxalic acid production, what we did is that we compared one fungus, filamentous fungus, Aspergillus niger, that is well known into an industrial context because that's a fungus that is currently being used to produce citric acid that you consume when you drink Sprite or Fanta, for instance. And then we compared the oxalic acid or the low molecular weight organic acid production to a yeast that is called Meierosima guillermondi, and that has been initially isolated from a geothermal brine. And we wanted to see whether this yeast would be more adapted to this kind of context. And we did this in a bioreactor. So I just wanted to show this picture because that looks a bit like a jam that you have forgotten in your fridge. And that's actually how it looks when you grow a filamentous fungus, Aspergillus niger, in a bioreactor. And then what Gillian did here is that he first compared 3 types of nutritive conditions for oxalic acid production. He first had a nutrient-rich medium where the production should be optimal. Then he took what he called the brine-like medium. So instead of using water, he used a geothermal brine as a solvent and just mixed it with the carbon source, but no extra nutrient. And then he did a combination of both where he had nutrient and then the impact of salinity. And then he measured in these 6 conditions that you can find here 4 different types of organic acid, obviously oxalic acid, but then citric acid that is also very common in this organism. Remember that I told you that Aspergillus niger is a model organism for citric acid production, and then gluconic and malic acid that are also very common in fungi. And then he measured their concentration over time, and very importantly, here you see the purple curve of oxalic acid. You see a sharp decrease. This is only an artifact because he has been doing the batch into different reactions, so that you sample the filter out and add new biomass so that you can use twice the bioreactor for production. And what you can see here is that, and that was a bit expected, is as our strain of Aspergillus niger, which we know is optimal for oxalic acid production, is indeed optimal. That's the most prominent organic acid being produced. And then when you compare in the optimal condition to Meierosima, you see that unfortunately Meierosima is quite lousy at producing oxalic acid. Then we look into the brine-like medium, so high salinity, carbon, but no extra nutrient. For instance, there is no nitrogen, no phosphorus. Here, that was also expected, but we wanted to try. There is very few organic acid production, and then when you add nutrients, you rescue a bit the production of organic acid, but the fact that you have this salinity seems to have an impact on oxalic acid production, because here you see for Aspergillus niger that you produce much more gluconic acid. But there we have a baseline, and we know that in optimal condition, we can produce up to 8.5 grams per liter of oxalic acid. Then the next step of Gillian was to assess different type of carbon sources that are considered more low cost in order to, if you want to transfer this into an industrial process, in order to have something that is a bit more economically viable. This he did in flask, not in a bioreactor environment. So this is a bit suboptimal, but for screening is much more effective. And there, what he compared is again saccharose, because this is the most optimal carbon source. And he compared this to milk whey, glycerol, beet molasses, brewer's spent grain, and cornstarch, which have different type of prices and have different type of metabolizable status, and then different type of nitrogen. And that's a lot of graph, but I just want to, so if you look on the left side of the screen, you have organic acid production for the different type in lines for the different type of substrate in presence of the optimal nutritive condition in terms of nitrogen and phosphorus. And then when you have no nitrogen and phosphorus, this is what we call the brine-like. And if we focus on oxalic acid, very importantly, what we see is, again, the nutrient-rich condition is always more optimal, whatever the type of substrate. And there are two carbon sources, glycerol, which you can see here, and Brewer's Spence grain, that seems to be the most promising alternative carbon sources to produce oxalic acid. However, it always comes at a cost, is that you have other type of organic acid that are being produced. And for instance, we have not yet evaluated whether this organic acid can also complex, for instance, calcium or sodium or lithium. Now, if you remember, there were 3 steps in our proposed biorecovery pathway, and the second one is to filter out what the elements we don't want in the fluid in order to recover something that is as pure as possible. And luckily enough, oxalic acid is, or oxalate, is a compound that is going to form complexes with many, many elements of the periodic table of the elements. And that's all the compounds that are circled in green or blue. This is going to form insoluble compounds at some point, and those that are here squared are those that are going to remain in solution. So this is what we wanted to do, is to see how much oxalic acid we needed in order to precipitate unwanted elements and keep, ideally, lithium in solution. So Gillian did this on 4 different types of brines, 2 brines that were actually provided, so actual brines that were concentrated for lithium. So there was 1 brine that was obtained by reverse osmosis, 1 DLE eluate, and then the 2 synthetic fluid of the project. So 1 that is low salinity and 1 that is high salinity. And what he did is that he added oxalic acid in increasing amount, and then was looking, and that's what you see here, when the quantity of precipitate was reaching a plateau, to which quantity of oxalic acid this corresponded to. So if you look here, for instance, you have a plateau at 17 gram per liter of precipitate, which corresponded to an addition of 10.98 gram per liter of oxalic acid. And of course, the quantity depends every time on the type of brine, and very obviously, the synthetic brine number 2, that is high salinity, I didn't highlight this here, but contains a lot of calcium, so very obviously, you need a lot more oxalic acid. And then, what you obtain after this oxalic acid step is you have a solid fraction and a liquid fraction. And what Gillian looked at is what remained in the liquid and what was transferred into the solid. And ideally, what you want is to have everything in the solid, but lithium that remains in the fluid. Of course, it didn't happen that way, but what you can see here, and that's the reddish curve, is in most instances you have the calcium concentration that is decreasing until it reached very low level. Please pay attention to the fact that here the scale is not the same. There is a scale for poorly concentrated element on the left side, and then on the right side you have a scale for more concentrated elements. So you have, in most cases, and that's the green line, you have lithium that remains overall stable. For instance, here in the concentrated fluid, here in the synthetic fluid, it's very low, synthetic one, so it's behind this pink curve, and here in the DLE, it has some kind of hectic behavior, and we don't really know why. But then, as I said, the aim is really to consider the 2 fractions. What you want to have is a transfer from the liquid to the solid. So here, that's a couple of graphs that represent the 6 elements we focused on. So calcium, the one we want to transfer into the solid, and then ideally we'd also want to transfer some of the potassium, sodium, and strontium, magnesium to some extent into the solid, so that lithium is the only one that remains into the liquid fraction. So looking at this fluid by fluid, what should happen here is a bit what you see here at the top of the screen. That's the situation for calcium, is that you have the blue fraction that diminishes and the red fraction that increases, and you would want to have lithium that remains blue. So first of all, those that are, so we did this assessment with ICP, and you would expect to have a line that is constant here. And what we had here, and that's pretty obvious for magnesium and strontium, is that we had an analytical issue. So we need to repeat those measurements. But overall, if you look at the trends, oxalic acid is really very good at filtering out calcium, but it very much depends on the type of fluids, and it works very well in the concentrated and synthetic fluid number 2, where you see that a lot of the calcium is transferred into the solid, and that most of the time lithium remains in solution. But then for other elements, that's a bit more hectic, and most importantly, sodium remains stable into the remains into the solutions, and that's something that is a bit of an issue for the further step. And that this further step is step number 3, where remember that then we have this clean fluid and we want to increase the pH so that we eventually precipitate lithium carbonate. And for this, we have selected an oxalotrophic bacterium that is called Pandorea. That's our own isolate. And this bacterium is actually pretty effective because within 8 days, it's able to change the pH from 6 to above 9. So that's, considering that that's a logarithmic scale, that's pretty effective. But one of the issues we have with Pandorea is that it only grows between pH 4 and 10. And this we have not discussed extensively, but if you look at the pH here, when you apply oxalic acid and you reach the plateau, you always reach a pH that is somewhere between 1 and 2. So what we need to solve now is to find a way to have an optimal activity for this bacterium, so that we don't add too much oxalic acid, so that the bacterium can not grow enough. So Elliot did this in his master thesis, is that he compared 3 conditions, one where he added abiotic acid, oxalic acid, then one where he added biogenically produced oxalic acid, and then another condition where he gave extra nutrient to the bacterium in order to see which one had the best activity. And he added only very small amount of organic acid so that the pH does not drop below 4. And what you can see here, and that's something that Gillian is currently investigating into further details, is that the condition in which you feed the bacterium with biogenically produced oxalic acid instead of an abiotic compound, you have this, you add oxalic acid, then the bacterium feeds on oxalic acid, that increases the pH. You add again oxalic acid, then the pH decreases, etc., etc. So that's something that is still, we are still not there yet. And then finally, what we managed to do is to obtain precipitate from our bacterium growing on lithium oxalate. And initially, we were very disappointed because the nice crystals you see here are not, so the geologists around here probably recognize that it's not a carbonate, that's a phosphate. So we managed to obtain lithium phosphate, and a bit like Enrico just showed, we were very disappointed. And then we discussed with someone saying that there is also an industrial interest for lithium phosphate. So we are probably now going to consider comparing both forms. The issue we still have at this point is that you see this nice phosphate here. They are covered by these nice needles, and those needles are sodium chloride. So we need to find a way to get rid of sodium chloride in order to be able to recover either carbonate or phosphate. So to conclude this microbial talk, even though we are still not at the pilot scale and we still have a lot of work to do to fine-tune the process, we still think that's a process that is realistic. because oxalic acid is easy to produce, and oxalic acid is really something to filter out, let's say, the elemental complexity of a fluid. But we still need to work on the step between adding oxalic acid to a fluid to clean it, and then have the correct conditions so that oxalotrophic activity can take place in order to have this initial pH that allows the bacterium to grow. And something that I didn't mention is that to allow obtaining these lithium phosphate crystals, we had to dramatically increase the concentration of lithium. So we need to work with fluids that are richer in lithium, that, for instance, the low salinity one. So definitely needing to work on something that is obtained from DLE or anything else. So I'm done. Thanks a lot for your attention, and to all the people that contributed to funding or working in this, obtaining this data.
Wonderful. Great. Thanks a lot, Saskia, for this great overview. I've seen many steps that needs to be like compiled together. Have you actually tried already that? Did you like put these like in a row from one to the other, where you can go through your cycle, let's say, with the different bacteria?
So that's one of the last steps that Gillian is going to do in his thesis, because he needs to hand out in December. But that's the last step he's going to carry out, is to try to have oxalotrophic activity on a fluid obtained, or from a fraction obtained from filtering out an actual fluid. And in another project, we are now trying to model the system in order to understand the limit, because sometimes running experiment takes a lot of time. So by modeling the system, we hope to be able to understand a bit what are the limits and how to move forward.
Okay, so still a little while to go, but you found a lot of things, and that I think is great. So are there any questions to Saskia? I can't see any. It's probably all a bit confusing for non-microbiologists to follow, but for me it was very fascinating. I think especially also the question that these other organic acids are produced. How do you are you planning to investigate that? Maybe they're even better for the lithium.
So that's typically something we will model very soon. Is based on the solubility constant of this organic acid. We want to explore whether another one is also more prone to chelate, and ideally to find something that combines to sodium or potassium, because that's, let's say, the most polluting element for us in the process.
Okay, very good. And I saw now there came a question in, probably to all three of you. Thank you for your insightful presentation. In your view, what are currently the biggest challenges in scaling the microbial extraction approach, or for Saskia, the microbial extraction approaches for lithium recovery from geothermal brines, from lab studies to industrial operation?
So I think the first step already, because if you looked at the numbers, to the quantity of oxalic acid that we need to be produced for a high salinity fluid is quite humongous. So I think that's one of the first challenge, and you cannot produce only with saccharose. So we really need now to fine tune a bit the quantity of oxalic acid that can be produced, for instance, by co-product of other industrial process. For instance, glycerol is a co-product of biofuel and these kind of things. So and then there are other challenges, because the oxalotrophic bacterium for me is also another challenge, because we tried to model how much alkalinity we needed to put in the system to go from pH 1.5 to 4, and that's also a massive quantity. So we will investigate other microbial alkalinizing processes to see whether we can reach the pH of 4 or find a strain that is able to be oxalotrophic at a lower pH. But for the moment, we haven't found any.
What about actually about scaling up? Like if you want to go to like if you really want to go to industrial level and produce a lot of those bacteria or fungi, is this a big issue or is it then
No,
once
so
you know?
just producing microbial biomass, I don't think that's an issue because there are a lot of processes that produce microbial biomass. I think it's more the metabolite we are aiming at that may be problematic.
Okay, good. That's good to know. That this is an easy step apparently.
Well, producing biomass is kind of okay.
Okay, so that's more easy than, for example, getting the pure manganese lambda oxide, for example.
But what is challenging is to have your strain doing what you want. Huh?
Yes. So you have to teach them.
Mhm.
Okay. So if there are no more questions to our three speakers, and I can't see any, then I want to thank all three of you, Enrico, Saskia, and Mustafa. And I thank EFG, Anita, and Maria for organizing everything. And I hope to see you all in the people from our project in our next project meeting, and of course the other people in the audience maybe for our next webinar. We don't have a date yet, but it will come. So have a good afternoon and a good
You
summer
too.
break
Bye.
probably.
Thank
Thanks
you.
a lot. Bye bye.
Thank you.
Bye.
Bye.
Bye.